podcast, Thomas Dietterich, Professor Emeritus from Oregon State University, take us to the depth of AI. So, stay tuned. This guy's good. Okay. So, welcome everyone to Future of Data podcast. Today we have with us Thomas Dietterich and a brief bio. So, he is a distinguished professor and emeritus and director of Intel Systems Research at Oregon State University. And Thomas has devoted his career to research in machine learning, starting from very first machine learning workshop in 1980. Along the way, he has been involved in 4 startup companies: Arris Pharmaceutical, MusicStrands, Smart Desktop, and currently BigML. He has made important contributions to learning with weak labels, ensemble methods, hierarchical reinforcement learning, and robust artificial intelligence. He was founding president of International Machine Learning Society, which runs the International Conference of Machine Learning, and president of the Association for Advancements of Artificial Intelligence. He has served on numerous government advisory bodies, currently is a member of the steering committee of the DARPA ISAT group. Dietterich earned his bachelor's degree from Oberlin College, his MS in University of Illinois, and PhD from Stanford. He is a fellow of the ACM, AAAI, and AAAS. With that, Thomas, welcome to the podcast.
Thank you. It's great to be here.
Beautiful. So I think very few times we got to meet someone who has a very deep inside sort of perspective on something that is to do with data and the future. And I think AI is one of the sort of things that we hear nowadays a lot. So why don't we, before we getting into this juicy stuff, walk us through your journey? Like, what brought you here?
Well, I guess I started in artificial intelligence when my primary motivation was really almost philosophical. How can we learn about the world? And in particular, how do we learn about it from our experience? And could we program a computer to do the same thing? But of course, from there, I got very interested in applied research. When I first started in artificial intelligence, the field was very much focused on toy problems, puzzles and games and things like this. And I was much more interested in making sure that the research I did would make a real difference and that I was working on the right problems. Because there was such a risk when you're working on a toy that you don't really learn anything important. And I think actually we're possibly seeing that now with the work on Go and chess, that people have, particularly in Asia, I think, have given far too much importance to these advances in Go. That the techniques are interesting, but they don't really generalize to the noisy real world, and that was the problem back in the 70s and 80s. So then I started working on problems in pharmaceuticals first on a sabbatical leave, and then from there I moved into problems in ecology. Because, of course, I'm interested in saving the world in general, but also Oregon State University is a leader in ecological science and also in conservation. And so I continue working in that area. I'm part of a network of people funded by the National Science Foundation called CompSustNet, which is about computational. Of course, I also was involved, as you mentioned, in MusicStrands, which started in the music recommendation space, then moved into sort of generic recommendations, and now is in smart finance. So startup companies themselves, of course, go on journeys. And then I've been involved in a smart desktop, which was an attempt to put artificial intelligence into as a sort of secretary for the desktop knowledge worker. And that was a spin out from a big DARPA program called PAL, the Personal Assistant That Learns. And probably the most famous spin out from that was Siri, which a group of people that had worked on the PAL program then built Siri as a follow-on project. And now I'm working on I'm a chief scientist of BigML, which is exploring machine learning as a service and trying to make machine learning extremely easy for people with no formal training in data science. So we try to make extremely easy to use tools for that.
Interesting. And in your journey, sort of when you saw this machine learning and AI field mature, I remember like a couple of decades back when you talk about machine learning and AI, it was so error filled that you can't rely any decision on your outcomes. So from your perspective, what has changed that has really energized this space?
Well, I think the two big trends are more data and more compute, right? And but I think also when the field first began in the 1970s, 1980 period, we had this idea that right. I mean, the origins of machine learning really are in the desire to program the computer to do certain things, like say computer vision or pattern recognition type problems that we as people find very easy, but we don't know how we do it. So, I always say if I wanted to build an accounting system, I can go interview an accountant and they can tell me, here are the steps you go through for each financial process. And I can just code those up and it's quite straightforward. But when I ask you, well, what are the steps that you go through to recognize this pen? And says, well, I don't know. I just recognize it, right? I don't first look for this and then this. It's not a procedure that I can code up. But of course, we can collect lots of training examples for that. And now that everyone has a camera in their phone or a phone in their camera, we have so many images on the net and we can crowdsourcing so we can get those labeled. And so that explosion of image data coupled with the advances in moving machine learning algorithms into GPUs and now specialized processors of various kinds has really allowed us to develop machine learning systems that can do amazing things. So yeah, I think those are the two main drivers.
Interesting. And help us understand the AI landscape now. So from your vantage point, what is AI and what are some of the segments that we can sort of divide this AI domain as such into? And if you can walk us through understanding what AI is.
Certainly. So, of course, AI is really a collection of software methodologies, right? It's not one single thing. What they all have in common is that we're trying to program smart software, right? And so at one extreme, of course, we talk a lot about machine learning, and there we're building smart software by basically imitating people, right? So we collect training data, we imitate what people do, and in some cases by aggregating many people, the data from many people, we can actually do better than the average person, right? But there's also another facet of artificial intelligence, which is really automated reasoning, and we see this a lot in automated planning, logistics, theorem proving, things like this. So for example, all of the device drivers on Microsoft now go through certain formal verification stages. Those are solving automated reasoning problems. And there are people that do theorem proving, and have found the computer has found proofs for mathematical propositions. The proofs are so long that people don't really understand them. But that's another instance of artificial intelligence that is very alien to human intelligence. And then there's a third area, I would guess, which is sort of knowledge representation, the knowledge graphs, these kinds of things, in which there's a huge amount of handwork. People manually build these large graphs, and more recently, people are trying to use machine learning to help with that. But these knowledge graphs are used, for instance, by Google to know what kind of an object, when you make a query, is this a person, is this a company, is this a place, and then they can choose an appropriate answer to give to you based on that. So I would say those are the three main strands: is building things from data, building things by hand, and then the automated reasoning Also, a very tight connection to optimization algorithms, which really got their start in the operations research field, right? But we find that very often a good way to program a computer to do something is to say, well, here is the goal that we want you to achieve, and here are the sort of component pieces that you could use to do that, the actions you could take, the subcomponents you could use in a circuit. Find a combination of these that achieves the goal. And this is somewhat what reinforcement learning is, in which you're taking sequences of actions, but it's also what happens in design and planning and logistics. And we like to say that we're moving along the what to how spectrum, right? So the how means I have to program each individual step and tell the computer how to do something. The what means I just have to say, here's what I want the computer to do, and it has to figure it out for itself how to do it. And we're finding that that what approach has, the advantage is that you can specify what you want at a very high level of abstraction. The disadvantage is that the computer will optimize exactly what you tell it to optimize, and if you tell it the wrong thing, then you get the wrong answer. So it's quite challenging to debug errors in that high-level specification. Whereas when you're giving step-by-step instructions, the computer will follow those instructions, so there are fewer risks there.
Interesting. And I remember that you were writing about, you written somewhere that what's most important in machine learning languages, sort of the methods by which the data was collected and labeled. Why do you think that? And if you can give us some examples on that.
Well, I think the usual assumption in the machine learning theory is that we have some performance task. Maybe one example might be that we're trying to predict where certain species of birds, where are certain endangered species of birds found, and we want our training data to have been sampled spatially and in time and space, so that we get a representative sample of possible locations, and then we can measure that. What happens I've been involved in this project called eBird, which is a big citizen science project where bird watchers, they're very enthusiastic. They go out and they collect checklists of the birds that they see. But they tend to collect those checklists close to where they live or along highways, for instance, or in campgrounds. And so, if you look naively at the data, you would think that endangered species really prefer to fly along freeways, right? Because that has been collected. So that's an example of sample selection bias. But we see it also you're trying to build a system to do medical diagnosis, but you take all of your data from, say, a hospital like Stanford University Hospital or Harvard Brigham and Young, a hospital where many of the customers are very rich, and you will get a skewed distribution of the symptoms, and things like just what's the weight and age of the group is very different. And if you try to take a rule that you learned in one of those hospitals and apply it, say, in rural Guatemala, it's going to be a total failure because you don't have a sample of the data that's representative. So that's another example. And then this comes up in issues of fairness in the criminal justice system, for example, right? This has been in the news quite a bit. We might want to have a computer system that makes recommendations to judges about whether a person should be allowed out on bail or be jailed. And if you use past data, you have a selection bias because you've only selected people that were previously in contact with the criminal justice system. And there's a lot of evidence that the criminal justice system is biased toward the poor and racial minorities. So you just, because the computer is learning by imitating what people do, it just copies what people do in that case, which is maybe not the outcome we want.
Interesting. So I think one thing that we hear a lot from sort of our interaction with a lot of businesses is so this idea of selection bias, right? So I think one thing that I was talking to someone that our best advantage is that we get bored easily. right? So that the very fact that if I look at a data and I say, hey, it's just I don't want to look at, so that makes us intuitively sort of cleverly make best use of our time. That means our intuition is kicking every now and then to help us sort of help us understand those things. But when you talk to data, anything you can throw at say AI, it just ingest, and the very aspect of it can never get bored gives us sort of leverage in, hey, let's just exploit it. But then, as you're rightly pointing out, that the selection bias creeps in, because obviously the more data it ingests, and sort of how the data was collected, what's the rationale behind the data and all that. So what is the resolve? Like, I think on the one side, the economics is amazing, right? With using machine and AI, right? I don't have like no food required, no oxygen to breathe. This just a system is running on its own, no sleep required. And on the other side, this world of creative, intuitive folks who get bored easily, lazy, lethargic, and all that fun stuff happening. So, what's your take on that?
Well, I guess I'm not exactly sure what the question is. I mean, clearly, automating sort of intellectual assembly line work, I think, is very important and helps. So, I'm familiar a bit with the work that's been done on trying to build computer vision assistants for people who look at pap smear slides, right? And every day, those people are given the glass slide with the cells on it, and they look through a microscope and try to judge which cells might be cancerous or precancerous, right? And this is a very difficult task, and they save all of those slides and they retest them as a way of getting an independent estimate of what the false negative rate is. So what fraction of the time do people miss a precancerous cell? And the false negative rates, at least the last time I looked at this, which is about 10 years ago, the false negative rates were shockingly high, like they might be in the 20% range. And this is one of the reasons that people are asked to have pap smears frequently, because in any one test, they may miss, the human analyst may miss the problem. So computer vision techniques were developed back in the 90s to basically look at all the cells on a slide and rank them by how suspicious they look, and just call the attention of the human analyst to the top ranked ones, right? And just by filtering out all the ones that you could safely ignore, you could make much better use of the human attention and get that false negative rate down to like 1% or something. So you can make huge differences by providing a tool that really helps the visual inspection type tasks to focus the human attention not on the boring normal cases, but on the interesting cases. People have done similar things. I was involved in a project at NASA JPL, right, where whenever NASA puts up a new instrument, say like the Hubble Space Telescope or something like this, they have lots of anomalies that are seen, right? And the early anomalies are typically various kinds of faults and noise, surprising faults and noise, like paint chips turned out to be a problem in the Space Telescope. But once they figure out those, then they're interested in the interesting data points. What the telescope might be looking at million points, but the scientists want to see, well, what are the interesting ones? And so working with my colleague, Kiri Wagstaff, she developed a system that would show people just what appeared to be the most interesting things. It really modeled all the boring stuff, and then it would say, what is the most uninteresting thing? The most unboring thing should be the thing I show to the analyst.
Interesting. So I think, you gave two fascinating examples, right? So one example was very sort of, healthcare, cancer detection, very monotonous job. Human error is very possible because, again, it's a monotonous job. And on the other side is predicting criminal, predicting which side of criminals would be, or figuring out the criminal justice system, because there are a lot of pending cases that probably AI could help with.
So an AI system would certainly be more reliable in the sense of being reproducible.
Right, right.
It will always do the same. It will treat all cases the same way. Now, it may be biased in the way it does that,
Right.
but it would. There's presumably a lot of variability across human judges that would be removed by using the AI system.
Right. So when you wear your researcher hat and you look at these problems, right, and some to from the business end, all they look for many times is the financial implication, right? So they'll save a lot of money and they can get a lot more done at a very reasonable pricing. What would you recommend to those guys? Like, how would I not put myself into where I'm predicting the criminals using AI vis-a-vis of looking at pap smear and figuring out if there's a sort of some concern or some health concern? Like, how do you evaluate if some criteria is ripe for AI or something is sort of that there's still a very high error rate and something? How would you evaluate those scenarios?
Well, let's see. I mean, usual rules of thumb are one, that people can do the task, right? Because if people can't do the task, then we worry that the data may not contain information sufficient for the task. And you can still try to use AI techniques to see if there's a signal there that people just don't observe, and that's kind of the story behind the whole data mining movement as well. Maybe there are patterns that aren't apparent to people, but the computer could find. But that's definitely a higher risk than going after a problem where we know people can do the task. The information is there in the signal, and then the challenge, then questions are, well, how stable is that signal, right? I mean, if you consider something like decide what stocks to invest in, you have a very noisy signal, right? That's constantly changing. Or if we think about, I don't know. Military applications also, right? There's that saying that that no plan survives first contact with the enemy. It's a very fluid and constantly changing space, or politics or things like this. But if it's something where the underlying process is really very stable, so we think about these cancer cases or recognizing handwritten letters, people are not changing how they write their letters very quickly. So we can expect that something we learn with machine learning will still be useful for a while, because the real enemy of machine learning is rapid change. So if I learn something that based on data from yesterday, and yet the phenomena has changed today, then my predictions will be wrong. So the more slowly things change, the better, because then we can retrain the system every day, every week, every month, and sort of track the phenomenon. And ideally, if it's not changing at all, then we just train it once and we can deploy it. So people's faces, in terms of a face detector, like is in all of our cameras now, people's faces aren't changing, well, maybe at evolutionary timescales. So that's a wonderful, stable phenomenon. My individual face, I might shave my beard or change my glasses or shave my hair or something, then that's more challenging, right?
Interesting. And that's fascinating. So walk us through your current research that you're working on. Like what are you working on nowadays?
Well, I'm very interested in questions of making AI more robust. I've watched, well, especially machine learning. I've watched machine learning, right, start with these complete toy problems where it was totally fragile. And then we've moved on to a phase, which I'd say up to the present, where most of the research is just focusing on performance metrics like accuracy, area under the ROC curve, precision at K, various metrics like this, lift and so on. And really not looking at the larger context, the software engineering context and the application context of our AI system. So we basically need to come to grips with the fact that people are actually using our technology, which we, for decades in the academic world, we've had the luxury of just studying the problems very abstractly and not really confronting the fact that, well, these systems need to be debuggable and maintainable, reliable, right? And also all of those sort of ilities, maintainability and reliability and so on, are things that have not been studied very much. So for example, I think every machine learning system should have a model of its own region of competence. That is, it should be able to say, given this new query, I refuse to make a prediction because this is outside the range of the data that I've seen before. So this is sometimes known as a classification with a reject option, and it's been an area that's been studied quite a lot. But in the era of deep networks, we need to revisit this question because a lot of our techniques, it's not clear how they can extend to the deep nets case. So, for example, you'd like to get well-calibrated probabilities out of your system, so that if you say, I think that I don't know, that this is a cancer cell with probability 0.8, then 80% of the time you say that, it should be true, right? That would be a well-calibrated probability. If you have well-calibrated probabilities, then you can set a cost threshold that, on the probability of error, and you can make a reject decision. The other problem that I'm interested in is the open category problem. So very often there could be some new kind of disease in our cells that we haven't seen before. But the way we train our machine learning systems is we assume the world is a closed world and there's only 10 possible digits in our writing, which is quite a good assumption. But in ImageNet, right, there are only 1,000 categories of objects, whereas we think there are probably hundreds of thousands of categories of objects. I had a project recognizing insects, trying to determine the species of insects from images. And we were focusing on a set of 54 categories of insects because those are used by the Environmental Protection Agency to assess the health of streams, freshwater streams. Right? If the stream is polluted, then many of the insects will be missing, or the distributions will be very different. So my collaborators went out and they collected 100 specimens from each of these 54 categories. We got beautiful pictures of them. We trained a computer vision system. It was getting 92% correct. But then we had forgotten to think about the fact that real samples drawn from real streams would have other stuff in them. Not just our 54 species, but there are 1,200 species of insects or something that live in the streams. Some of them are very rare, and also there will be false alarms like pebbles and sticks and leaves and things like this. And so when we took that into consideration, our equal error rates were something like 20 or 30%. So the system went from being usable to being unusable once we had to confront these novel objects. This is another area where I think we can use anomaly detection methods to say, does this input query look strange compared to the data we trained on? If it does, then maybe it belongs to a new category outside of the ones that we were trained on, and we should reject it because it's novel. Because we might be quite confident about it because it's far away from any of our decision boundaries, but it's also very far away from all of our training data, so we should really take care of it.
Interesting. And I was reading in your profile, you have also worked on reinforced learning. So what is reinforcement learning, if you can walk us through that?
Okay, so reinforcement learning really combines two things. One is sequential decision making. So let's take an example like playing Atari games or playing the game of Go or something like this, right? In the game of Go, you have to choose a sequence of actions to eventually win the game, and so that's in a perfectly closed world like Go. We could formulate it by just saying, well, here are the rules of the game, and here are the actions you can take, and just solve it. Try to solve it using search. But in the real world, we usually don't know the rules of the game exactly. So I guess there's a lot of work coming out of, say, Peter Abiel's group at Berkeley, where they're trying to train robots to grasp and pick up things. Right? You learn how to pick up a mouse, learn how to pick up a pen, all these things, and in that case, you want the robot to choose a series of control actions of all of its joints in order to succeed at some goal. And so you can have you can either demonstrate how to do that, which is known as imitation learning, or you can have the system try to learn by trial and error. It just tries random things until it succeeds. And once it has a successful case, then it tries to improve it. And so that's one thing. The other thing about reinforcement learning is that you only learn from what we call bandit feedback, or success or failure. So if it was a supervised learning task, I would say, well, the first action you should take is, I don't know, open your gripper, okay? And it would learn to open the gripper, and I would give it positive examples of opening the gripper and negative examples of opening the gripper. And I could teach it the first step. And then I could say, now you need to move the arm forward. And again, it could learn just to do each of those steps, and so on. And so you would teach it at each step what is the right action. But in reinforcement, it's usually too painful, too expensive to have people provide that kind of instruction. So instead, we just say, well, I'm going to give you a reward when you achieve the goal. I'll give you a reward of 100 points when you successfully pick up the pen, and otherwise I give you maybe a small cost penalty for each action you take, because I want you to learn to pick up the pen quickly. And so that becomes the reward function, and then we ask the learning algorithm to try to find a control sequence of controls that will achieve that goal, maximize that reward. So this is an example of what I was talking about earlier, where we are telling the system the what that we want it to do. We just say, well, the success is that you're holding the pen in your gripper, but we don't tell you the how, and it's up to the computer to figure out the how. And so I've looked at some applications in scheduling and logistics, where again we can give the system a reward for a good schedule that is short and achieves schedules everything within the allowed time and minimizing resources. And I've looked at problems in, say, invasive species management or wildfire management, where you want to try to achieve some goal like killing off an invasive species, and there's a cost to each action that you do, so you want to minimize the costs or achieve the cost in the shortest amount of time, subject to some budget constraint. So these kinds of things.
Interesting. And you have also said you're working on anomaly detection nowadays as well. I think what's going on in that space, if you can walk us through that.
Well, so anomaly detection is interesting because I think it's been relatively poorly studied. I mean, if we compare it to supervised learning, classification, regression, object recognition, speech recognition, all these things have thousands or tens of thousands of researcher years invested in them. But anomaly detection is relatively poorly studied. There has been an active community, especially more on the industry side, and so I'm trying to get more academics interested in developing the underlying theory. But people are interested in anomaly detection for a whole host of reasons. One would be often you build a control system. Like, for instance, one application of reinforcement learning is to managing data centers, right? You want to decide when you can power down a system or put it on standby because you don't need it, and you want to save energy. You may be managing the air conditioning systems of the building. Maybe you're managing the network infrastructure, and all of these actions. But you also want to have some sort of an anomaly detection system that is saying, is something strange going on? Has there been a spike in network traffic? Is there unusually warm temperatures in some part of the room that might indicate broken equipment, might indicate an intrusion or cyber attack, or it just could indicate a change in the mix of jobs that we're being asked to do that maybe should require some management response. So we've looked at we had funding to look at sensor networks, so particularly weather station networks, right? You have these weather sensors, and they get dirty over time, or they may break because they're exposed to extreme weather. I joke that if we would just keep these weather stations indoors, they wouldn't break. But but so I like to say the Internet of Things is going to be the Internet of broken things, because you have all these sensors, and often they're cheap, and so they tend to break, and they're often in challenging environments. So how can we detect those broken sensors? Well, we can build a machine learning model of what we expect their readings to be normally, right? So if we're looking at, I don't know, traffic sensors, we can have a model of traffic. If we are looking at weather sensors, we can have models of weather. And we can even use weather forecasts in that. And then when something unusual happens, like a weather sensor stops varying and just is reporting a flat line, or it's very spiky noise, that shows up as a statistical anomaly that's very unlikely according to our model of the normal behavior. So there have been some very interesting algorithms. Unfortunately, I didn't invent any of them myself, but some very interesting algorithms that have been developed in the data mining community that with a relatively small amount of training data can develop pretty good anomaly detectors. And so we've been paying a lot of attention to fraud and computer security applications, because I think we've recently realized that in artificial intelligence, computer security is really a complete showstopper for us. If cyber attacks, AI systems provide new attack surfaces like data set poisoning and adversarial queries. And unless we can solve the cybersecurity side of that, we really can't use the technology. So we've been looking at cybersecurity applications, and there we have applied these anomaly detectors to look at events or traffic. When we see an anomaly, then in these systems, typically you have some analyst, like security analyst, and you want to show them these cases and ask them, is this something that you should act on? And so you have to show them the case, and you have to give them some kind of an explanation. Why do we think it's anomalous? We may be measuring 200 different attributes of each event, but we don't. It's not sufficient to say this one looks weird to us. We want to say this one looks weird because of attributes 12 and 17, and here's a scatter plot that shows it's a real outlier. So then the analyst can say, yes, that is a problem, and I'm going to act on it, or no, that's a false alarm. We want to take that analyst feedback back into the system and make the system more discerning, because the big problem with anomaly detection is false alarms. No anomaly detector is perfect, especially if the natural phenomenon itself has heavy tails, and so there will just naturally be outliers. So what we're finding is that by incorporating expert feedback, we can double or triple the number of correct true anomalies that we discover for the same amount of analyst effort in answering our queries.
Interesting. Now, I want to have some of your perspective on the enterprise adoption of this AI, like how businesses are using this AI from your vantage point. So, what are some of the things that you have seen that businesses get it wrong? They get it wrong about what the capability of AI and what AI could do to help their business. Like, what are some of the things you could share?
Well, I think two big mistakes. I think one is that people attack a problem without asking whether really machine learning, like supervised learning, is the right solution. So it's not enough to say, well, gee, we have all this data. There must be something we can do with it. Again, you need to identify a task where you think the data really has enough information in it. There's information content that you'll be able to get accurate predictions out of it. So just mere quantity is not enough. As we were saying before, the stability of the phenomenon needs to be stable so that it can be predicted. Otherwise, the cost of ownership will go up, because you'll be constantly having to make changes to the system to track the phenomenon. I guess the other problem is thinking too narrowly. So you can think of say maximizing click-through rates in advertising, and you can say, well, I want to get the guy to click on this ad right now. but it's important maybe to take a longer term perspective and look at, say, the lifetime value of that customer or the long term value of that customer. If they click on something and then they're very disappointed because it really wasn't something they wanted, then they feel sort of tricked and disappointed, and they're not going to click again in the future. So that suggests that instead of thinking about it as a supervised learning problem of they click or they don't click, and I want to predict that, and then I want to show them the ad they're most likely to click on, that would be the sort of supervised learning formulation. We should really think about it as more of a sequential decision-making or reinforcement learning problem. We want to look at their value over the next year or 2 years or 5 years or something like that. And we want to present them with a sequence of experiences that will turn them into a loyal and repeat customer. And so it's really important to think about what is the optimization objective that you're giving. I mean, we've now seen, with things like YouTube, right? There was a story that came out last year that showed that they had asked the recommendation system of YouTube was tasked with maximizing user engagement, as how long could we keep the user online. But what the AI really learned to do then was to give them more and more extreme videos that were more and more compelling, which was sort of, I think someone said you start out looking at car videos maybe with the idea of buying one, and eventually you're looking at high-speed crashes and catastrophes, right? And we have to ask, so it's sort of like a built-in radicalizing thing. Are we really optimizing the right objective in these systems? And so I think stepping back and looking at the big picture is very important, because the big weakness of our AI technology is that it is extremely narrow. The computer really doesn't understand the broader context at all, and it will just optimize the thing we tell it to do, and it will do that well, but that may not turn out to give us end-to-end, return on investment or long-term financial outcomes that we want.
Interesting. Thank you for sharing your perspective on that. So, one thing I was thinking about when you were talking about robust AI system, and if I wear my statistician hat, so I think when many of these models were created in the past, we were not dealing with too much data, right? So they were like, numbers were not in billions and trillions. There was no petabyte of data that we have to deal with, and obviously the math worked during that time. But now because of scale and because of our, as you said, more computing and more data, we are now, every number is so skyrocketed high that what's your perspective on the evolution of error bars? Like now with more data, there would bound to be more sort of errors that or sort of recalibration that you needed from the legacy mathematical models that were created then. So what's the resolve? What's your take on that?
Well, it's a little difficult to say, because of course with more data become more opportunities. And so our desires for what we would like the systems to do also scale. And then we may end up with the fact that although if we're instead of looking at a population of 10,000 people that come to one store in one city, we now want a model that works over the entire world. Or we're doing online e-commerce, and so again, the whole world is coming to our doors. And then the heterogeneity of that population means that we need lots of data for every subgroup within the population. And so we have to check whether we have big data imbalances. So the raw numbers about the total number of data points we have might not be telling us about these sub areas. And so tools that people are exploring right now really try to find what are the segments of our users that are most poorly represented in our data, and how could we get more data for them? So big data problems often turn out to be thousands of tiny data problems. Of course, you hope that there are some things that can be shared across that whole area, and that brings us into the area of meta learning or transfer learning or hierarchical Bayesian models. things like this, where you do try to get that sharing across the different subgroups. So yeah, I guess that's my first answer. In terms of trying to get accurate error bars out, there is quite a lot of progress on this. So unfortunately, right, if we look at something like random forests, we can get very nice error bars out of those, because those are an ensemble method, and it's almost a quasi-Bayesian procedure, so we can get posterior estimates of quantiles, of means and variances, all kinds of things out of those things. But and in principle, one could do the same thing. If you trained 10,000 neural networks for a problem, then you would have an ensemble of those. It's just that's even with our supercomputers, that is a huge amount of time and energy to spend. So that's the challenge. In some sense, the math still works, but it's not feasible at the scale that we want to operate. So obviously, people are looking at things like, can we use dropout as a simulation of an ensemble? Are there can we use other techniques that are more explicitly Bayesian? Can we post-process the data in some way to say, using a model, probabilistic model such as a Gaussian process in the final layer of a neural network, and which would give us maybe some error bars. There's work on just rescaling the softmax temperature has been shown to give better calibrated probabilities. So it's a very active research area right now, I guess.
Interesting.
The other thing, of course, that's been very disturbing is this discovery of adversarial examples in computer vision. So when we have, it seems very high dimensional input, that all of our data points are really very far apart in data space, and so there's a lot of empty space in between. And it also seems that that we train our systems discriminatively, that is, to make the discriminative decision that we want. They seem to learn the minimum statistical information, in some sense, the minimum sufficient statistics to do that task. And that turns out to be very non-robust, right? And again, ensembles would probably help, but maybe we need to think about more descriptive or generative models rather than discriminative ones. And this is one of the reasons people are so excited about generative adversarial networks, deep density estimators, variational autoencoders, these kinds of generative models, which in which the system doesn't just look for the minimum information necessary to distinguish between a chair and a desk, but says, well, here's what chairs generally look like, here's what desks generally look like. And so one can imagine the systems of the future use our discriminative techniques to come up with hypotheses, and then validate those hypotheses by using a generative model to check that there really is something in the image that looks like a chair, not just something that had these minimum features for telling a chair apart from a desk.
Interesting. And what about what's your thought on how AI is impacting the current workforce? So if we sort of, from your vantage point, you're seeing how AI, we talked about pap smear analysis, how much jobs will it displace, right? So what's your take on, if I am a sort of listener or viewer watching this podcast, how would I secure my future? Like, what would you suggest as a scientist?
Yeah, I guess I have two or three. I mean, first of all, machine learning techniques rarely automate everything in a job, right? So it's more like with the pap smear case, we can give the pap smear inspector a better tool so that they can do their job better. Now, it's true that we probably would need fewer people then overall, and but it's not as though we can automate away radiologists and all of those medical professions. We still need all those people, but maybe we don't need as many of them, but we need all of those professions. A second thought is that the technology is creating new jobs as well. It's very hard to know what those are, though. I'm personally a terrible forecaster of the future. Back in the around 1982 to 84, we rolled out the internet, right? I was a graduate student at the time when the ARPANET went from the protocols it had been using to adopt TCP/IP, the Internet Protocol Suite. And everybody congratulated themselves and said, "Okay, computer networking, we've achieved it. Now it'll be easy to move files from one computer to another computer, or to do remote logins, and the problem is solved." We had no idea that we conceived of computer networks as a way for computers to connect one computer to another computer. We didn't realize that the big impact of the internet was to connect people to people, business to business. That was totally just inconceivable in 1980, and yet 13 years later, the web browser was developed and it's had support for images. And my first reaction was, who needs images in when you're using a computer? So I'm terrible at that. Now my son is a web page designer. Okay, a job that never existed. So it's very hard to predict where things will go. One thing I'm really struck by is how much I would say. There are lots of machine learning tools that actually don't do their tasks very well, but creative people are turning them into tools. So if you've seen the Deep Dream synthetic images that you can get out of neural networks by running them backwards and saying, take this image and transform it to be as cat-like as possible, and you get all kinds of strange things emerging. And people are doing this with music. In almost every creative endeavor now, in design, people are training machine learning systems to, in some sense, do a straightforward prediction task, but they're not using it for that task. They kind of run it backwards and use it to ideas and possibilities. So, it's turning out to be a powerful creative tool for people to use. So there's another example of a totally unexpected outcome. And then I guess the third thing is, we tend to think about AI systems in terms of their knowledge of the physical world, right? And there's a lot of focus nowadays on robotic manipulation. Can I learn to pick up a pen, and locomotion and things like this? But I think a huge amount of our human knowledge is actually not so much about the physical world as it is about the social and emotional worlds. So our emotional intelligence and our social intelligence, what has really allowed us to be such a successful species is our ability to work together and to form organizations and institutions and things like this. Our computers are social idiots, right? There is an area of multi-agent systems research that tries to make them, it's sort of more like distributed computing, making multiple computers work together. But I suspect that any job that involves social and emotional intelligence is going to be safe from automation for a very long time. Because a characteristic of those areas also is that they're very context-rich. And as I was saying before, our AI systems continue to be extremely narrow in their capabilities. So we can build, the joke used to be that back in the 70s that all of our AI systems were idiot savants. That is, brilliant at one thing, like playing chess, but they couldn't do anything else. And our new technologies still have that problem. Now they can play chess much better, but they still only can play chess. The big advance is we can take the same software tool and retrain it to play Go, but it can't play chess and Go at the same time, right? So we can have a so-called big switch. We can have hundreds of these different systems and switch among them, but we don't have a kind of general purpose intelligence, what people sometimes call artificial general intelligence. We don't have really very many good ideas about how that works or how we could achieve it. So that's a long-winded answer to the idea that the human versatility and our ability to have an appreciation of the broader context in which a decision is being made is absolutely critical. And it's the reason that we can expect man-machine combinations to be the wave of the future, because the machine may be able to do the narrow task very well, but it's the human that has to bring the broader context, because the computer just does not have that broader context.
Interesting. So I was just thinking about, so one of the conversation I had with a philosopher a couple of weeks back, and it went in a very interesting direction, and definitely I want your perspective on it. So his perspective was that, Vishal, the problem with AI and human intelligence is the very definition of intelligence. And his perspective was, what we use when what we are told to be intelligent, like I am intelligent because my ability to, right, so learn a skill and learn to interact around my surrounding and doing certain things. Now in the construct of AI, the definition is like it's more of a classifier problem. Hey, is it still a cat? Is it still a cat? Like, how it's still a cancer? How probable are you that it's a cancer? So his perspective was, what if you change the very aspect of that? Hey, it's not intelligence; it's something else. So humans are not threatened by this word called AI vis-a-vis of human intelligence, and sort of they don't feel, and they feel it as an empowerment sort of tool. So I want your perspective as a practitioner. What's your thoughts?
Well, certainly many groups have tried to get away from the AI term. I mean, because intelligence, Marvin Minsky used to say the word intelligence is a suitcase word. That is, you open it up and it's got all kinds of stuff inside. It's not just one thing. So there are many, many different ways to be intelligent. We've talked about sort of recognition intelligence, that I can recognize objects, and that's some sort of very fast neural process to which we devote a large part of our brain. And then there's sort of problem-solving intelligence, that I can come up with a sequence of actions that will achieve a goal. People actually are not very good at that kind of planning to achieve goals, right? And we think about like doing algebra or doing mathematical proofs. People are really terrible at this, but we think the people that can do it are very smart. But the computers can be much smarter than people in that area. So, but that's totally different from this kind of visual recognition intelligence. So where am I going with this? Certainly, our AI systems, we're not building right now, commander data, some sort of freestanding agent-like thing. And in Hollywood, there really seem to be only two stories. Either it's the commander data story, which is basically the Pinocchio story. He wants to be a real human and have emotion. And that's very flattering to us, but I don't think it's very realistic.
Right.
Or it's the Terminator story, right? And maybe it's really probably more the C-3PO story, right, which is our sidekick assistant that has some unique characteristics, but also is very different from us in many ways. So I think that some people have tried to say, well, we should call it augmenting human intelligence, or human aware intelligence, or centaur systems where it's a man plus machine or man plus place. I think all of those are possibilities. We really want things that help us be more human and help us be more successful and more effective, right? And because we're building the future for us, not for our computers.
True, that makes sense. And so, what is your crystal ball prediction for next 5 years in AI? Like, what do you expect to see, or should we expect to see in the next 5 years coming out from the AI camp?
Well, I think in the next 3 to 5 years we will have good solutions for the self models. So our machine learning systems should be able to have good models of their own competence and be able to tell when they're going to make a mistake and when they aren't. There continues to be lots of progress on pre-training networks that then can be used with a relatively small amount of data to do new tasks. So we already see this with the computer vision systems that are trained on something like ImageNet, and then they can be very rapidly retrained to recognize insects or or cellular, or cancers or things like this. So these systems are learning some kind of general representations or useful features of images that are independent of the particular task. There's a very exciting paper that just came out this week showing similar things for training bidirectional language models, where they could use these pre-trained models then on a wide variety of different tasks and achieve new state-of-the-art results, advance the state-of-the-art on several of those tasks. So that seems to be an area where we're making progress. Another kind of closely related area that is super important in robotics and in reinforcement learning in general is what we call sim-to-real transfer. So reinforcement learning generally is extremely slow and extremely data hungry, right? Like taking millions and millions of trials to develop a good grasping strategy or something. So this is infeasible in the physical world, but in simulation, and it's very so. But the problem is, of course, the simulated world and the real world are not the same. Despite all the discussion of having a digital twin of your plant or your car or whatever, it's not a twin. It's some sort of a poor substitute. But we're getting better at understanding how we can train in the simulator and then transfer that to the real world with a small amount of additional training in the real world. And I think the real leader in this is Sergey Levine and Peter Abiel in the Bay Area are doing beautiful work on this in robotics. But we're seeing it in several other areas as well. So those are the things that give me hope that we can move beyond these massive labeled data sets, and being able to learn quickly with smaller amounts of data, and that also means quickly adapt as the phenomena change too. So maybe that'll allow us to tackle problems that are more dynamic and less static.
Interesting. Beautiful. So thank you so much on walking us through that. So now we're at the tail end of the conversation. So I want your perspective, your personal perspective on, and this is we ask all of our guests to share is, if what are some of the traits in your life that has really helped you be what you are today? What would you attribute those qualities or those traits to?
Well, I guess probably number one is that I'm a very curious fellow. So I think anyone who's working in data science, you need to be committed to learning, working with a subject matter expert and really learning some of the knowledge about the domain. You can't become a subject matter expert, but maybe you're a professional dilettante. You have to learn the vocabulary, the concepts, the challenges and threats in each application, and really to formulate the problem properly, right? Is it really a prediction problem? Maybe it's an optimization problem. Maybe it's a sequential decision problem. Are we observing the true state of the system, or do we have noisy observations and we need to estimate the state of the system? All these kinds of decision analysis type questions, modeling questions. So I think it's very important to be curious and to really revel in learning new things. And so that's definitely me. I guess another thing is it is also good to be a bit obsessive about methodology and getting things right. Any software engineer needs to do this. That you need reproducible processes. You need to document what you're doing. Learning how to improve your own process every time you take on a new project. So you need to sweat the details. And then I guess the third thing, the big advice I give to students is, learn as much mathematics as you can, because it's something that's hard to learn on your own. But different parts of mathematics have turned out to be very important as the field has evolved. Back in the 70s and 80s, people were talking about, well, maybe we don't need to teach calculus to computer scientists anymore. Now everybody has to know about derivatives, and everyone has to know about probabilities, and and it's very important to understand about convexity and convex optimization and so on. So particularly more on the R&D side, you need that strong mathematical background. So I would say maybe those are the three things: curiosity, a bit of compulsiveness about the data, about methodology, and then having a strong mathematical background.
Interesting. And what are some of your favorite reads, some of the books that you would like to recommend to our listeners and viewers?
Ooh, I didn't prepare a good answer for this one. Well, I think the book that was most thought-provoking to me most recently is a book by Paul Charest called Army of None, about autonomous weapon systems, right? Because this is an area that I think a lot of us are very concerned about. And one of the things he points out in that book is that generally when people use an autonomous system, the autonomy has a fence around it. There's a certain narrow area where the system is allowed to act, and outside of that area, it's not allowed to act. And a key question is, how do we specify that region of autonomy? How do we enforce it? How do we test it? Things like this. The other thing I thought that was most important in that book was his emphasis on the importance of the human organization that surrounds any application of artificial intelligence. You know, as a technologist, I tend to focus on the technology and want to make the technology reliable. But if we want the company or whatever the organization is to use that technology reliably, then the whole organization needs to be reliable. And there was a lot of research after the 3 Mile Island nuclear quasi-meltdown that occurred. An area of research came up known as the research on highly reliable organizations, or high reliability. Social scientists studied human organizations that are very reliable in their decision making, like nuclear submarine crews, for instance, have an amazing reliability record. Air traffic control, surprisingly reliable. Even nuclear power plant management, surprisingly reliable. And certain military groups, some are more reliable, some much less reliable. And so there are many characteristics of HROs, high reliability organizations, is one, they pay attention to anomalies and treat those as a threat to their reliability. In other words, they don't say, well, that kind of thing just happens from time to time. No, they try to figure out why. Another thing is that they push decision-making authority down to the person who has the knowledge. So the person who's really knowledgeable about the particular problem makes a decision, not the manager. And so those are two examples. Of course, they have to do training and so on. So I mentioned all of this. I really recommend this book, and I think there are a lot of lessons in there far beyond military systems to just any application of AI technology. You want to make sure you have processes and procedures and a human organization around that ensures that the whole system is reliable. It's not enough for the software to be reliable by itself or for the humans to be reliable by themselves, but the combination needs to be reliable as well.
Interesting. Thank you for sharing that. So now at the last question. So as a closing remark, like what would you like to suggest our listeners and viewers if they want to take away from something from this conversation, from this session? What would that one message be that you want our listeners and viewers to take away?
Well, I think it's very important to remember that that software, including machine learning software, is all software. So really, AI technologies are just another way of building software. So they have all the problems that software has. That it's very hard to build the right software system. So you need to have agile methods where you can revise the system, and they're hard to test. But so testing is very important. Right, and so all of the issues that come up in software, cybersecurity, privacy, all of these things apply to AI software as well. In addition, AI software maybe introduces some new problems. So a big issue with machine learning is we don't know how to prove that the machine learning system is correct. With traditional software, the programmer writes the main line of the code and really thinks about the general case. And where human programmers fall down is on the corner cases. And we uncover those by probing the system with test cases, right? I mean, we just train the system on test cases, and there's no general specification of what the system is supposed to do. There's nothing we can verify against. And so that's a unique challenge, I think, that machine learning systems pose that traditional systems don't. So my main take-home message would be: it's still software. It has all the problems of software, and then it has a few new ones as well.
Awesome. With that, Tom, thank you again so much for your gracious time helping us understand the depth of AI, what it is doing, what it could do, what to expect. I do appreciate your time with us. You're always welcome back on the podcast. And whenever you are in Boston, let me know. Love to meet you and share a beer or coffee or lunch with you. So thank you so much.
Okay, well, it's been a pleasure talking with you, Vishal.
I thought I was sick of home, but actually I was homesick. Never really knew that I would have to grow up so quick. I'm so uncomfortable, don't know anybody here. Just a couple dudes that I met once, that's it. And I go into the booth feeling nervous. Got butterflies in my stomach like I'm so worthless. Is the mic on? I don't know how to work this. Inside I'm breaking down, I hope I'm not up on the